Today we are going to do the topic electricity. And the first heading that we are going to deal with is charge. The reason why we did periodic classification of elements and atomic structure in the beginning is because we'll know some basics of the chapter, as we are going to deal with charges, atoms, electrons. That is the reason why we did those portion earlier. So we now know that the body which gains electrons becomes negatively charged and the body which loses electrons becomes positively charged. So, thus there are two kinds of charges. Number one, positive charge, and number two, a negative charge. We also know that two like charges like positive charge and a positive charge will repel each other, while two unlike charges like positive and negative, two different type of charges, two unlike charges attract each other. The charge on a body is denoted by capital Q. The charge on a body is denoted by capital Q. So, the SI unit of charges Coulomb, denoted by capital C. And Q is equals to plus minus of NE. Where N is the number of electrons, comma, E is the charge on an electron. The value of E is 1.6 into 10 to the power minus 19 Coulomb. Okay, so one electronic charge is 1.6 into 10 to the power minus 19 Coulomb. Then let's find how many electrons will require to make up 1 Coulomb. So plus minus is because if there is an excess of electrons, electrons are negatively charged, we'll take the minus sign. And if there is deficit of electrons, that is if the electrons are lost by the body, it will become positive charge and will denote by a positive sign. So Q is equals to Ne. Let's say Q is 1 coulomb. We are checking how much electrons or how many electrons will require to form 1 coulomb of charge. So N into E is 1.6 into 10 to the power minus 19 coulomb. So 1 by 1.6 into 10 to the power minus 19 is N, or we can say N is 1 by 1.6 into 10 to the power minus 19. That is equals to 10 to the power minus 19 goes to the numerator, becomes 10 to the power 19 by 1.6. That is equals to 10 into 10 to the power 18 by 1.6. We remove the decimal, we get 0. So 4 4s is 16, 4 25s are 100, 25 by 4, 4 6 are 24, decimal 1 in hand, so 10, 4 2s are 8, we have 2 in hand, because of the decimal we get another 0, 20, 4 5s are 20, so 6.25 into 10 to the power 18 electrons. So 1 coulomb of charge is produced by 6.25 into 10 to the power 18 electrons. This number is huge. So even small 1 coulomb charge, we need so many electrons. Okay. Now we come to electric current. Okay, so what does current mean? We know that in a dam, when water is left, we say that there is a water current. Water current is basically water flowing in a very high speed. So current, or say when air flows, we say that there is a current of wind or current of air. So current basically movement, it shows motion. So electric current is basically the motion of electrons. So let's first see what an electric circuit is. A continuous and closed path of an electric current is called an electric circuit. Okay, I'm making the diagrams with pen, but you make sure that you make it with pencil. So I'm making it with pen so that you have clarity in viewing the diagram. Okay, this is our bulb, this is our ammeter. We'll come to what an ammeter is in some time. This is the key or the switch and this is, see, one is called a cell. This is a combination of cells. It's called a battery. Whenever we have a combination of cells, we call it a battery. And in a battery, the longer one is the positive one and the smaller one is the negative one. Since this ends with the smaller one, this is the negative terminal of this battery, and this ends over here with the longer one. So this is the positive terminal of the battery. Here the key is open. Open means this is not plugged in. We have not switched on the key. So in this case, electric current does not flow. So we say that the circuit is open, or this is an open circuit. Electric current does not flow because a continuous and closed path of electric current. So we needed a closed path. This is not closed, hence it is called an open circuit. And so this denotes the key or the switch that is closed. So now this circuit is complete and it is closed. Hence what happens is the bulb glows. So this is a closed circuit. Electric current flows and the bulb glows. And the direction of current is taken from the positive terminal to the negative terminal. It starts from the positive terminal and goes towards the negative terminal. So this is the direction of electric current. So we saw over here a thing called key or the switch. So let's see what the definition of switch is. A conducting link between the cell and the bulb. This is the switch. It is a conducting link. If the switch is open, that means the current will not flow, and if the key is closed or the switch is closed, then the current flows. Okay, so let's define the electric current now. So electric current is defined as the rate of flow of charge with respect to time. So in charge, we learned that the charge was denoted by capital Q. Here, the current is denoted by capital I. So I is equals to Q by T, where Q is the charge flowing through the circuit, and T is the time taken. Current is a scalar quantity. The SI unit of current is ampere. Denoted by capital A, named after the French scientist André Marie Ampere. So the SI unit of current is ampere. 1 ampere is 1 coulomb, the SI unit of charge, by the SI unit of time, that is second, which is equals to 1 coulomb per second. So an instrument called ammeter is used to measure electric current in the circuit it is always connected in series in a circuit through which the current is to be measured. So this is a series connection where there is no joint in between, that this does not separate each other. So this is called a series connection. We'll see what a joint is. If there would have been a joint in between, then there would have been a chance that the ammeter would go in parallel. But here the ammeter is in series, as there is a no joint. That is no separation of two circuits. This is just one single circuit, hence it is connected in series. Okay. Now let's come to the question that why metals conduct electricity and non-metals do not. So the reason for this, you can recall that electrons are deficient in non-metals. Non-metals need electrons to complete their outermost shell. So that is the reason why they are not readily losing electrons. But metals have 1 or 2 or say 3 electrons in its outermost shell, and they are very readily available to lose electrons. Metals lose electron to form positively charged ions, and non-metals gain electron. So non-metals do not release any electrons, whereas metals release electrons. So a metal has a large number of wandering electrons as they lose electrons, and an equal number of fixed positive ions. Metals, basically they lose electron and form positively charged ions, and when we say metals, we are considering solids. So these solids have very little intermolecular spaces between them, hence they are fixed positive ions, whereas the electrons after being lost are free to move and hence are wandering electrons. So when a metal is formed, its atom lose electrons from its outer orbits and the positive ions do not move. Why? The electrons move almost freely inside the metal. These electrons are called free electrons, and because of the presence of these free electrons, metals are able to conduct electricity. Okay, so we know that electrons move. Let's consider a circuit again. This becomes our ammeter. Positive, negative, and say we have a key, and the key is closed. So in this, the electrons will flow. This is our positive terminal and this is our negative terminal. So as we know, electrons are negatively charged and the negative terminal will have excess of electrons. So we see that there are excess of electrons in this terminal. So electrons will flow from their excess and go towards the least. So positive charge is produced by losing electrons. So they are deficient in electrons and they have excess of electrons. So electrons move from the negative terminal towards the positive terminal, So this is the flow of free electrons. And we know that current is said to move from positive towards negative. And why do we take the flow of current from positive terminal to the negative terminal is because electrons were not known at the time when the phenomenon of electricity was first observed. That is why when it was first observed, the people who observed electricity said that the electric current would move from positive terminal to negative terminal. Hence, conventionally, we take the flow of current from the positive terminal to the negative terminal. So this is the flow of electric current. Though the flow of free electrons is from the negative to the positive, but we take the flow of electric current to be from the positive terminal to the negative terminal just because the electrons were not discovered at the time when the phenomenon of electricity was observed. Okay. Take this as a note that conventionally in an electric circuit, the direction of electric current is taken opposite to the direction of flow of electrons because electrons were not known at the time when the phenomenon of electricity was first observed. Okay, so the next topic we are going to discuss is the potential difference. Before that, let's see an example of how we find solution using this formula. So let's take an example. A current of 0.5 ampere is drawn by a filament of an electric bulb for 10 minutes. Find the amount of electric charge that flows through the circuit. Solution. Given current I is equals to 0.5 ampere, time t is equals to 10 minutes, which is equals to 10 into 60 seconds. So that is 600 seconds. So therefore Q is equals to, we know that I is equals to Q by T, therefore Q will become I into T. So IT, that is equals to 0.5 into 600, that is 300 coulomb. So the unit of charge is coulomb. So the answer will be coulomb. So next we come to the topic electric potential and potential difference. Okay. To define potential difference, let's look at the image. Say this is a positive charge, and say you have a point B and a point A, and you are bringing a positive charge from point A to point B, say a positive small charge, say Q. So the potential difference since this is positively charged and this is also positively charged, when you bring this positive charge from A to B, what will happen is these two will repel each other. So to bring this close to B, you will need to do some work in bringing a unit positive charge from A to B, as you are bringing a positive charge towards a positive charge, which are likely to repel each other. Hence the potential difference between 2 points is equal to the work per unit charge in moving a positive test charge from one point to the other. So, like electric current was denoted by I, charge was denoted by Q, so we will denote potential difference is denoted by capital V, and V is equals to W by Q. The SI unit of electric potential or electric potential difference is a volt, denoted by capital V, named after Alessandro Volta. an Italian physicist. So 1 volt is equals to 1. The SI unit of work done is joule and the SI unit of charge is coulomb. So 1 volt is 1 joule per coulomb. Potential difference is a scalar quantity. In fact, most of the quantities that we'll be dealing here in electricity chapter will be scalar quantities itself. And the potential difference is measured by means of an instrument called the voltmeter. The voltmeter is always connected in parallel across the points between which the potential difference is to be measured. Okay, let's look at this again with the help of a diagram. Say we have a bulb over here. An ammeter is connected in series. We have a key, the key is closed, and say we have a battery. So this is the positive, negative. Electric current flows from the positive terminal towards the negative terminal. And say we need to check the potential difference across this bulb. So what we'll do is we'll connect the voltmeter in parallel to the bulb. So by connecting voltmeter in parallel to the bulb, what happens is whatever voltage difference that we find over here, the reading of the voltmeter, will be the amount of voltage consumed by this bulb. That is why this voltmeter is connected in parallel to the bulb. An example relating potential difference. So, how much work is done in moving a charge of 2 coulomb across 2 points having a potential difference of 12 volt. So solution, first we'll write what is given to us. So the first thing that is given to us is the charge. So charge is equals to, say, Q is equals to 2 coulomb, and potential difference V given to us is 12 volt. The SI unit of potential difference is volt. Volt is also denoted by capital V itself. So potential difference V is 12 volt. Therefore, work done W is equals to, as potential difference V is W by Q, so W will be equals to V into Q. So this is equals to V into Q, which is equals to 12 into 2, that is 24, and the unit of work done is joule. Try keeping all the units in the SI unit itself, so that when you get the answer, you can also write the answer, final answer, in the SI unit itself. Okay. Next, we'll look at some circuit diagrams. First, an electric cell. So an electric cell is somewhat like this, where the longer one denotes the positive terminal and the shorter one denotes the negative terminal. Just one of this is a cell, but whereas if we take a combination of the cells, we call it a battery. Third one, plug key or switch. So first let's draw an opened one. An open one looks like this. And a closed one looks like this. Number 4, a wire joint. This one that we see here is a wire joint where a wire was coming and it separates in two directions. So a wire joint looks basically like this. We just bold the portion wherever the joint is. Number 5, wires crossing without joining. So suppose here the wire is going and from up there is a wire going. So we cannot show this in a diagram by just directly drawing a straight line, is because there would be no difference between a wire joint and this one. That is why what we do is, as we come near it, we show that this is going from the top and going straight there. So this denotes wires that are not crossing, that are crossing but they are not joining. Number 6, an electric bulb is denoted by this. Number 7, a resistor of resistance R. We'll come to what resistance is in the next class. For now, just remember that this denotes a resistance R. Number 8, variable resistance. We can also vary resistance in certain case. This variable resistance is possible with the help of an instrument called rheostat. This instrument is called rheostat, which is denoted by, we denote normal resistance in this way, And what we do is we bring a wire and we point it like this. So this point basically denotes that we can vary it. We can move this point over here or here by moving this. So as we can vary the resistance, hence this is variable resistance, and the instrument is called rheostat. Number 9 is an ammeter. Ammeter is denoted by a capital A in a circle, and this ammeter is always connected in series. Number 10, we have a voltmeter. Voltmeter is denoted by a V in a circle and is always connected in parallel to the circuit. With this, we come to the end of this lecture.